The selection committee is pleased to name Dr. Chelsea Harris as a 2019 Frederick A. House Scholar in Computational Science. Dr. Harris received her PhD in astrophysics from the University of California, Berkeley in 2018, and is a postdoctoral research associate in the Department of Physics and Astronomy at Michigan State University. Chelsea was selected for her demonstrated leadership, character, and outstanding technical achievements in computational science. Chelsea's doctoral research focused on understanding the physics of supernova explosions of stars and, in particular, modeling how supernovae interact with the surrounding gas. Her work has produced the entire electromagnetic spectrum of emissions from these events, yielding a powerful probe into the nature of the star system that exploded. Chelsea's research went far beyond previous analyses, which were based on relatively simple analytic models that assumed a smooth surrounding medium. Her more realistic numerical models predict important differerences in the expected radioluminosity and timescale, with implications for deriving constraints on the density of the surrounding material. For example, Chelsea's work revised previous estimates on the mass of circumstellar material by a substantial amount for the type 1a supernova PTF11K, one of the most important and studied star explosions ever observed. Her work has also helped explain the slow decline in X-ray emissions in another supernova, leading to multiple awards of Hubble Space Telescope time to confirm new theories via observation. Chelsea is a computational astrophysicist making outstanding contributions at the interface between theory and observation. She has positioned herself to be an impactful scientist in the current era of large astronomical data sets and high-performance computing simulation. Chelsea has also distinguished herself as a leader of great character. She has demonstrated independence and perseverance in long-term projects, and it is clear to her collaborators that she places a great deal of importance on scientific integrity, prioritizing accuracy, precision, and clarity. Chelsea also is dedicated to effective scientific communication, delivering well-crafted presentations that are humorous, pedagogical, and scientifically fascinating. One example is the Science of Star Wars lecture she gave at UC Berkeley to more than 100 local community members and children. I kind of was hoping you were going to give that talk, but.
You're not children, so.
Well, you've not spent enough time with me. She also generously shares her knowledge to the benefit of her colleagues and always is willing to take the time to help them. Finally, Chelsea was a strong advocate at UC Berkeley for breaking down the stigma associated with seeking mental health treatment and made sure students were aware of the services available to them on campus. The impact Chelsea had in her department was significant. Mental health topics are discussed openly in faculty meetings and students are not afraid to seek help. Addressing this important but often neglected issue took courage, and that Chelsea did so demonstrates her proactive nature and leadership. Chelsea Harris is a computational scientist who not only excels technically, but also serves as a role model for others, as both a researcher and a human being. She embodies the qualities Fred House promoted in all early career scientists. Let's congratulate Chelsea.
So this is not only different from the previous talks, although cells will be involved as resolution elements, but it's also very different from my PhD work, which was all about supernovae, so giant explosion followed by giant crash. This is giant explosion with giant laser. So I don't know why explosion isn't enough for me, but this is kind of how my work goes. And I'm part of this team. The PIs of the project at MSU are Sean Couch, Andrew Chrislieb, and Luke Roberts, who represent an astrophysics component, a computational science component, and a nuclear experiment component. So it's this really exciting collaboration at MSU, funded by the DOE. So just an outline of my talk. Hopefully, you'll see by the end the overarching theme that I'm implementing this high-order magnetohydrodynamics code module in the Flash code to explore jets in supernovae, stellar explosions. But first, I'm going to talk to you about the cool things that I'm now a part of since graduating and getting my PhD, because I think that is something I was always interested in when I was a fellow. And then I'll go over the background of making jets in a supernova, just the foundations for my work. And then I'll kind of explain this SparkJoy module that's the high-order magnetorotational hydrodynamics that I'm implementing. So first, a dog-based look at what I have joined. When I was still a PhD student, I learned about the Department of Computational Mathematics, Science, and Engineering at MSU, and I thought it was really exciting. If you look at sort of their mission statements of the CMSE and the CSGF, I think you'll see that the keywords are really similar in that they're seeking to kind of put your money where your mouth is in terms of bringing an interdisciplinary approach where scientists who are more problem focused in terms of domain expertise for how to apply an algorithm would then be able to link up with someone who is developing that algorithm to really make sure that you're using the best thing for your science without having to necessarily be an expert in all numerical methods. So I really wanted to become a part of CMSE, and when I was on the job market, there was a position open to do the science that I'm going to talk to you about, and that is why I moved from the Bay Area, which is like 70 degrees in late winter, to Michigan, which was 33 degrees in late winter, and I thought, oh, it's such a nice day, I should open the door and really like revel in the outside while there was still snow on the ground. So it's been kind of a big move, but it's been worth it, and the project that I joined in order to kind of explore this department is the TEAMS project. It's a SciDAC grant that spans really the entire nation, and it stands for Toward Exascale Astrophysics of Mergers and Supernovae. So this is a very unique effort in computational astrophysics, especially supernovae, where we're really trying to bring together basically everyone who's doing any part of physics having to do with a core collapse supernova or a neutron star merger, neutron star black hole merger into the same room to do code comparisons and talk about how do we bring our codes, these legacy codes, up to the performance that they need for exascale in the future. And you see it really does span the whole nation here of continental United States. Okay, so let's get to this background stuff about making jets in a supernova. This is my favorite artist's interpretation of a star exploding, so I always show it. But what a supernova really is a star being ripped apart by a shockwave in less than 1 second, which I think is kind of sad because it's spent at least like 10 million years or something getting to where it is or longer, and then in less than a second it all ends. There are different ways that you can get this kind of explosion, but the commonality is that the way that we see them is through the radioactive isotopes that they generate. So nucleosynthesis is really key in supernovae just from the get-go. So this is a supernova remnant, the Crab Nebula, that I'll bring up in my talk, several times. But the different contexts that supernovae are used in astrophysics, there are many, but just a few are that they're the endpoints of stellar evolution. So for testing our theories about how stars evolve, we need to study supernovae. They create and disperse heavy elements. They energize the galaxies. And they are used actually to measure the expansion history of the universe. So really on all scales of astrophysics, you can use supernovae as tools to get at the core physics that you want to explore. And in today's talk, I'm going to focus on the creation and dispersion of heavy elements and core collapse supernovae as the sites of our process element creation. So what are our process elements and why do we care about them? This is a plot of, do I have a, yeah, okay, well, it's kind of faint. This is just a plot of the atomic mass versus its versus its abundance, and this is the solar curve. The most abundant elements are hydrogen and helium that were formed in the Big Bang, and then everything up to iron can be made through fusion in stars and supernovae pretty easily, and then dispersed through supernovae pretty easily. But then beyond iron, because of its stability, you really have to just like throw neutrons at these guys, and then they'll stick and create the heavier isotopes and elements. And so we have all sorts of elements beyond the iron peak, but they're much less abundant than anything up here because you need these different processes. And what's talked about a lot is the S process and the R process elements. So just taking a closer look at that, what is an R process element? That is one that's formed by rapid neutron capture, so you need a very neutron-rich environment. So if we just look at the same plot, basically, but just zooming in on that high mass end, you can actually separate out the S process in purple from the R process in green. And what we find is that there are certain elements, like platinum and gold, that are predominantly made through the R process, which means that if we want to explore where these come from in our simulations, we have these elements that we can look at as very good tracers when we want to compare to the real world. But the thing about the R process is just from the physics, it requires a really neutron-rich environment. So when you're thinking about where could this be made, a giant ball of neutrons starts to really come into play. So the best candidates for the R process sites then are neutron star mergers, which will then create these elements and disperse them in the dynamical ejecta, or the core collapse supernova itself. And you want to study supernovae for either of these processes because they're actually the site of neutron star creation. So this is why the team's focus is on mergers and supernovae. It's really, you could rename this into what's up with the R process, because that's kind of our focus. Okay, so core collapse supernovae create neutron stars. This is the Crab Nebula, and this would be the picture that you would be most familiar with if you know this nebula at all. This was seen to come from a supernova. So we have, from cultures across the world, we have data on this from 1054 AD in our calendar system now. So here's like a Chinese log that tells us about the timescale of the brightness and decline. And then this is the Anasazi Native Americans back from the Chaco Canyon. They did such amazing astronomy. It's ridiculous. I'm so excited to visit one day. And they're showing the position of the supernova relative to the moon, so we can correlate that with the position of the Crab Nebula to know that this was a supernova. Okay, so definitely Crab Nebula, supernova, and then with our modern instruments, we're able to look into the core and see this pulsar wind and these jets. So we know that there's a neutron star at the center. So like neutron star from core collapse through observations, not just theory. It's for real. Okay, so this got us really excited early on, before I was born, so I don't know why I'm saying us, but the idea that you have this proto-neutron star surrounded by all these neutrons, and then outside of that, you have all these heavy nuclei that could be seeds for the R process. And people were like, awesome, R process. But the problem is that you don't just have this environment, you also have these neutrinos. And what the neutrinos will do is actually convert the neutron-rich material into proton-rich material, which then isn't good for creating the R process anymore. And this is where jets come in. So not only did the numbers not make sense with, if all core collapse supernovae made R process elements, we'd have way too many of them. So people were already like, maybe not. Then this comes in and it says, maybe not. But then jets, okay, this is what jets will do. They're basically come with me if you want to live for our process elements. You get created, and then before anything can happen with the neutrinos, you get sucked out at almost the speed of light and carried away from that site where now you are safe to continue living. Actually, you'll radioactive decay into other things, but whatever. So now this is sort of why jets are being looked at as, if core collapse supernovae create our process elements, then it would be these supernovae with jets, which are also more rare, and so then you get the abundances making more sense as well. So that's really the motivation for studying jets in core collapse supernovae. And you can see that this is a simulation from Philip Mosta from 2017, and they're matching the solar abundance pattern to various simulation nucleosynthetic yields, and you're getting like a pretty good match here in that europium region. So this is pretty promising. So how do you create a jet in core collapse supernovae? That's kind of the next question. So we know for sure that core collapse supernovae have jets because we see them, the association with long gamma ray bursts and type 1c broadline supernovae. We think that you need magnetic confinement to really narrow the jet and push it out of the star, which is kind of cool because stars already have magnetic fields, so that's something else we know. But the problem is that you need to amplify these magnetic fields a lot. And so that's the key, is finding a process that within like 10 milliseconds can boost your magnetic field by over a factor of over 1 billion. But this is a simulation that I don't know if you'll be able to see. This is, again, Philip Mosta showing the amplification of the magnetic field through an instability that I'll describe. So the magnetic field is lower in the dark red and then higher in the saturated colors. And what they actually see develop in their simulation is a jet-like structure and a dynamo in the core. And the simulation is only 133 kilometers on the long side. So you can see the time up here. We're at about 10 milliseconds, and we've already developed a nice, really strong colloidal magnetic field that can potentially launch a jet in the supernova. The problem is that, as I'll explain, we have resolution limitations, so we can't actually follow this to really long times where it's actually going to start trying to escape the star. So like, does this jet survive? Does it escape the star? Does it actually carry out the elements that are being produced? This is all stuff that is really limited by our need for high computational power and resolution. But the basic physics, because I decided I was going to try to teach you guys physics today, of why we're amplifying the magnetic field is something called magnetorotational instability. So in a system where you have like a disk around that's gravitationally bound to an object, you get what's called a Keplerian orbit. So this is a very simplified version of the physics. And if you're in a Keplerian orbit, then if you are at the inner radius, you're moving faster, but you actually have less angular momentum. So you have speed increasing inward, but angular momentum increasing outward. And this would be rotating like this. And you have this neutron star at the center. And then you have a magnetic field being threaded through this rotating disk, so that inside it's basically going vertical. Okay, so I'm going to show you a side view and then a top view, and we're just going to look at two little fluid elements that are on the same magnetic field line. Okay. So this is how they're going to start out. This is like the perfect system. They're just on this straight field line. But if they get slightly perturbed, so like in the same radius, but just a slight perturbation in the angular direction, the magnetic field wants matter to stay together. And it's like a rubber band connecting these fluid elements. So what it's going to do is it's going to say, OK, you need to slow down. You need to get energy taken away from you so that you can come back in line. You need to speed up. You need to get energy put into you so you can get back in line. But it's a weak magnetic field, so it can't actually enforce this behavior that it wants to enforce. But it tries anyway, like a big dummy. And what happens is that by taking energy away from this guy, the orange guy, this one now has to move inward to a place that has the angular momentum that it has. And this one has to move outward to a place that has its angular momentum. But out here is slower, and out here in here is faster, so their separation actually increases. And that means that it's an instability, right? Because your initial perturbation is going to keep growing, and the magnetic field is just going to keep trying to do this because, you know, physics, like, it doesn't have any sense. So what happens is that you get these big channel flows. From an initially small perturbation, you can get these big ordered channel flows. So this is the original work from Balbus and Hawley in 1991, if you want to like look up more about it. But your initial colloidal field, even the colloidal component, actually gets amplified, which is like when lines get squeezed together, that's the magnetic field strength, right? Gets amplified, and also you develop a toroidal field from this type of instability. In the core collapse context, the fluid dynamics are much more complicated. You don't have these really nice disk structures. So for a while, people weren't really sure if the MRI could actually function in these systems. And so that's where a lot of work has gone into. And so now I'm going to talk to you more about like specifically trying to simulate the MRI. Okay, so it kind of comes down to a resolution issue because, as I said, this is an instability that starts small and then becomes big. The equations that govern it, which I decided to show just because I know some people in the room are not like me, where they're like, I need cartoons. They're like, I need equations. So the governing equations are the conservation laws for density, momentum, energy, and the magnetic field. You have the no magnetic monopoles constraint, and you have some equation of state. And so like this work by Obergaulinger, for example, you always have to choose a rotation profile and stuff, so I just wanted to choose this one example, where you have omega as the rotation profile, this n will be a buoyancy term, the r is a differential rotation term, and you can come up with a stability criterion that just depends on those parameters. And then calculate the scale of the fastest growing mode, lambda fastest growing mode, which depends on the Alfvén speed, and then these two terms. And the important thing is that what they find is that this length scale can be like 7 kilometers, which is much smaller than the scale of the entire star. So before I had shown you something that was like 133 kilometers on a side. So this is possible to get several resolution elements, several cells. I promised I'd say cells. So you can have several cells spanning this wavelength. But you can't do the whole star because this is so small. but you can get a growth time that's like 10 milliseconds, which is good. And then the growth time will also depend on these different parameters, the magnetic field strength, the density, and the rotation rate. And so what people do in order to achieve the MRI in their simulation is that they will artificially change the rotation rate or profile from what a stellar evolution code is spitting out, and or they will just be like stronger magnetic field. So the assumption is, even though you can't resolve it, there already was the MRI, and so it's already amplified the magnetic field. So we'll just like kind of basically start from somewhere in the middle of the physics that we're interested in. And it's just a compromise based on the computational limitation. So we already have a way to do magnetohydrodynamics in Flash with the Spark module. So the Spark module it's in Flash, so you can do AMR. The Flash is AMRX for teams. And then you do a Wino reconstruction to get, if you have the cell like centered values, right, you need to do a reconstruction to get what it is on the face in order to compute a flux to update your solution. And then the time step is explicit Runge-Kutta. And we can see jets in this work, but this isn't published, so I never really advertised this, but we get jets with Spark. And so then when I came on board last year, the idea was to make Spark high order, because right now it's at this second order bottleneck. And the reason that we want high order, so the motivation for SparkJoy is that things like numerical viscosity depend, like you can reach a numerical viscosity that you want with lower resolution if you have a higher order code. So that's important because, as I'll show on the next slide, the viscosity can become a numerical resistivity that affects your MHD. And then also, basically more bang for your buck. You get a higher accuracy, lower error for the same resolution. And so for something like the MRI, where we're really worried about whether or not it's accurate because we're trying to launch a jet here, people, then we want this higher order method when we're going to the exascale machine or just these larger simulations that we want to be very high fidelity. So what I was just saying before is that this same paper, Obergaulinger et al. 2009, found that these channel flows, so this is the magnetic field as a heat map, and this is the spatial coordinates. These channel flows actually will get disrupted by the numerical resistivity, even though the equation that you're solving for is ideal and doesn't have any resistance. As we all know, the computer is just like, yeah, but in a Taylor expansion kind of way, don't I have resistance? So it just introduces that in for you and creates these turbulent flows, which are also physically important, but not for jets, so I'm not really going to talk about it. But this is another interesting thing about lowering your resistivity. So the components of SparkJoy that, again, I'm doing in pictures, we're implementing an algorithm that we did not develop, and I am not developing, and I would be terrified if you asked me detailed questions about it. But the basic components are we're trying to work with conserved variables, which is already a change from what Flash had before. It's a constrained transport method where you use the magnetic vector potential instead of the magnetic field itself so that you ensure the divergence-free constraint of the magnetic field. Since we're, again, using Flash, Andrew was like, you guys should really just do finite volume because it makes more sense when you change the resolution at the boundaries of the different resolution. So we're trying out finite volume, whereas Spark was finite difference. We're still doing reconstruction. We're doing this fun little thing for doing multidimensional fluxes, where you basically just like weight the values of the fluxes that are around you, as opposed to doing something like Gaussian quadrature points in each cell. And then again, it's an explicit Runge-Kutta method. And I wish I could show you results, because I worked really hard to get something for this conference. But of course, because I was trying to do that so hard, the code was like, nah, So I have right now just a talk killer bug, and I have some instability. I think I have like an index somewhere that I'm like setting to like the +1 of what it means to be, which sucks because I have like 5 different for loops that this could be in as a conservative estimate. So this is the current on-fire status of SparkJoy, and I'm sorry, this is kind of just how it goes, right? But I thought this is an opportunity because one of the things for the House Award, which I was so honored to receive, I am so honored to receive, is that I talk about mental health, and I was debugging, and I was like, there's a mental health message in here. Yeah, I thought you guys would get it. I thought you'd know where I'm coming from there. So as I'm debugging, I'm thinking like, this IO stream, isn't this sort of like feelings? Yeah, it got really derailed, you guys. But like not really though, because really, your brain is constantly processing information and trying to make sense of it, right? And the equivalent of this IO stream is, so these are all like warning messages that you can't read, but I have so many of them every time I try to compile the code. And someone once saw it and they were like, whoa, that's a lot of errors. And I was like, he's like, I can't believe you have to fix all those. And I was like, those are warning messages, so I fix them by ignoring them. And I was like, that's so much like our feelings. When I was in grad school, I just had this like crippling anxiety, and when I decided I should probably take care of this, the first thing they taught me was you need to start paying attention to your body. You are getting, this tension in your chest. No one said this, but they were like, there's gonna be something that's telling you you're getting anxious. And I learned it was tension in my chest. And so, you have a physiological response to feeling something. And that is like this, your body is constantly like, hey, something's wrong, right? And just like errors, sometimes you think that the thing that's wrong is something else than it actually is because the error messages kind of suck, right? Not really helpful, but it's helpful to know that it's there sometimes, because if you can pinpoint oh, that interaction happened and now I feel this way, that will really help you to not really make a mountain out of a molehill, I think. But obviously, everyone is different and has different context, but I thought, okay, this IO stream thing, everyone might get this if I present it this way. And I just wanted to really hit on this fact that basically you get this constant string of messages from your brain that we're kind of encouraged to ignore and just focus on your work, keep your head down or whatever. But we really work in this environment where you have this prolonged stress. Your PhD is basically 4 to whatever years of just constant stress and worry about your future and your work. In our field, STEM, we tend to really devalue the impact of human interactions and kind of think that oh, we're all an ideal gas system with no particles interacting, and it's not a good approximation at all. We prioritize criticism over validation, right? Because it's really important for science that you're looking at everything really analytically and critically, and that you're not essentially getting confirmation bias. It's really important when you are doing science. But the problem is that we also do that just to each other, where it's not about validating or criticizing the person's science, but you really start to do it to the person themselves. And it can be hard to find an environment where you're not in an echo chamber, but you're still getting validated. And that's really important to your overall sense of community and happiness and well-being. And then added to all of this is the blur that you get between the work that you're doing and your own self and self-esteem and self-identity, which is very natural in a creative process like science. And also, this isn't just something you value your work and therefore there's a blur between yourself and your ego and your work. It's also the very real thing of implicit bias, where people also will see your name and judge your work based on your name, and that makes no sense, but it totally happens. And all of these things combined, plus any other factors in your life, are really bad for mental health, and it's really not a surprise, I think, to anyone, even though we don't talk about it, that every study that is looking at the mental health of scientists finds that we're really bad at it. We have way higher rates. Usually they'll study something like depression, or we'll talk a lot about imposter syndrome, right? They'll focus in on one thing that can be measured or be cured. And they find that we always have significantly higher rates of these things than the general population. And I think it makes a lot of sense when you look at the environment that we're in and the kind of types of people that we are in terms of being ambitious and then around amazing people constantly, which is great, but also really stressful sometimes if you don't have the right headspace about it. Okay, that was longer than I thought it would be, and I'm so sorry. So just to sum up, Yeah, obviously now you guys are totally focused on the fact that I am implementing high-order magnetohydrodynamics to explore jets and stellar explosions. And I kind of told you about the things that I joined that led me to this project and kind of away from my PhD work, but that's fine because I'm really excited about what I'm doing. And why it's really important for us to study how to make jets in a supernova, and then a little bit of detail about this SparkJoy framework, which I hope you guys understand is totally based on Marie Kondo and her nested box framework for getting high order. All right, that's it.